Okay, so it's a very great pleasure for me to introduce our today's speaker, Pavel Volkov. So he is a new faculty at the University of Connecticut, and as you know, we have a very good tradition that if there is any new faculty in the broader Providence region, which extends pretty far from here, of course, then this faculty must come here and make a condensed matter seminar. Now, Pavel got his PhD in 2018 from the University of Houghton in Germany. Then he spent 4 years as a postdoc at Rutgers, another year at Harvard, and since 2023, he has been an assistant professor at the University of Connecticut. His research interests are pretty broad, so much of the work he did is on superconductivity, as well as on various types of topological matter and very many other things, especially non-equilibrium physics. And today, as you will see, we'll get a talk that combines many of those topics. You see topology and phase transitions and superconductivity in the title immediately, but I suspect that the most interesting thing hides behind the word beyond. So let us welcome Pavel.
Thank you very much for the kind introduction. I've been enjoying my visit here, and I will indeed mostly talk about twisted nodal superconductors. And at this point, while the field sounds complicated, it actually matured enough that there's a review paper that we wrote. And I will also, given time permitting, I will say a few words about the beyond, which are the directions which were kind of motivated by this research on twisted nodal superconductors, but go beyond that. So this has been a largely collaborative effort. I started working on this topic back at Rutgers, and I've been continuing to do so, collaborating with a group of Jan Pixley. The experimental results that I'm going to talk about have been mostly performed by Frank Zhao and Alex Q in the group of Philip Kim, with samples coming from Brookhaven in collaboration with IFW Dresden. And also on the interpretation of the results, we collaborated with a group of Marcel France at UBC. And the beyond part has been done in collaboration with a postdoc in my group, Paul Eugenio, as well as a group of Ashwin Vishwanath at Harvard. So the context for what I'm going to talk about is the emergence of field of Twistronics, which is basically the simple idea of taking two-dimensional materials and stacking them with a twist, which turned out to open broad opportunities to realize correlated states, topological states, etc. It all, of course, started with twisted bilayer graphene, but since then, many other platforms have been realized, multi-layer systems or transition metal dechalcogenides. And the general idea of, I think, at least summarized called those materials, is that you take a semiconductor or semimetal in one layer, so you stack them with a twist, and then you suddenly start getting correlated and topological states that were not present in a single layer. The idea I'm going to explore here is that can we actually start with materials that at the single layer level are already correlated? They are superconductors. And if we take superconductors already at the level of single layer and stack them on top of one another with a twist, can we get new physics? And of course the answer is yes, and specifically, unlike that case, what you're going to get are topological and time reversal breaking superconducting states. Okay, just a light introduction, which also will highlight the differences with other platforms, because unlike the other platforms, which can be at the single layer level to a good degree described by just band theory, here we cannot do it, and the reason is the presence of superconducting order. So as we know, the presence of superconducting order means that there is an expectation value, an order parameter present, which sort of describes the condensate of pairs of electrons. And roughly one can, there's a lot of information hidden in this order parameter. Specifically, there's the relative motion of electrons within a pair, and then there is the collective motion of the pair as a whole. So this order parameter is related to current, specifically at the center of mass motion of the Cooper pair, or the complex phase of the Cooper pair as a function of the total coordinate of the center of mass coordinate is related to superconducting current that goes on without the dissipation. And the relative motion of the Cooper pair describes sort of what kind of orbital the two electrons are forming. And in most superconductors, we know of the ones that are described by BCS theory, those pairs are isotropic, a little bit like the ground state of the hydrogen atom, S wave, but they can also be pretty anisotropic, and for example, the wave function of such two electrons can be sign changing. And that's what I'm going to focus on in this talk, because precisely the properties of such superconductors are greatly affected by twisting, which is kind of already obvious from this picture. This kind of order parameter is not invariant under twist. Okay, so we have the superconducting order parameter. That's one big thing present in superconductors. But there's also, of course, electrons. And electrons in a superconductor, their energy is greatly reconstructed by the presence of this order parameter. So the way to understand this is to go to momentum space, where original electrons without superconductivity have some kind of a Fermi surface, and inside this Fermi surface, all states are occupied, outside all are empty, so this is the low energy manifold. Once you have superconducting pairing, basically what you end up with is opening a gap on this Fermi surface where no excitations can happen below a certain energy, and if your order parameter, its relative wave function is sign changing, so will the sign of the gap at the Fermi surface. And specifically, as it changes sign, there will be particular points on the Fermi surface where the gap closes. And if you really work this out, taking the dispersion of electrons, the dispersion of holes, and the pairing between the two by the superconducting order, you find before long that expanding around those points, the Bogoliubov-de Hamiltonian, you find that the low energy quasiparticles behave as Dirac fermions. So that gave essentially some initial impetus for us to work on this problem, because we have layers that have Dirac fermions. These Dirac fermions are not electrons. They're some kind of superpositions of electrons and holes, but they're Dirac fermions, and we can twist them, and maybe we can play the same game that people played with twisted bilayer graphene. There's also, of course, experimental motivation. So this Dirac code can be basically directly visualized with angular result photo emission in the superconducting state of so-called BISCO, which is one of the high TC cuprates. And I think this beautiful figure really illustrates the correspondence between theoretical expectation and what you see in experiments. So there's a linear dispersion in both directions. The red line is the Fermi surface. So both perpendicular to the Fermi surface and along the Fermi surface, you see a linear dispersion, which characterizes a Dirac code. Importantly, unlike graphene, this is a very anisotropic Dirac code. Those two velocities are by no means the same, and they're actually order of magnitude different. The other motivation comes from the fact that precisely the same material, being one of the most two-dimensional of the high TC cuprates, is to a certain extent exfoliable. It's not as easy as with graphene, but already in 2019, it has been realized that you can take one monolayer of this material, which actually contains, for details, two superconducting planes rather than one. Well, that's crystallography, but it's still single unit cell, thick layer of that material, and it superconducts, and you can almost see no difference between superconducting properties of the monolayer and the bulk. Okay, so I've introduced two basic elements. Each superconducting layer has an order parameter, and it has electrons, which, affected by the order parameter form Dirac quasiparticles around specific points in the Brillouin zone. And in principle, it's all an interacting problem. Order parameter affects the quasiparticles, quasiparticles affect the order parameter. But what I'm gonna do for simplicity in the remainder of the talk, I treat the properties of these two objects a little bit separately. So first, I'm gonna focus on what happens in a twisted interface of such unconventional nodal superconductors, what happens with the order parameters. And in the second part of my talk, I'm going to talk about what happens to the quasiparticles. The assumption behind that is that the coupling between these two order parameters and quasiparticles across the interface is weaker than the intrinsic scale of superconductivity, which is okay for high TC superconductors where superconductivity is really strong. Okay, so I'm going to start with the part which is mostly connected, which is most connected to the experiment at this point.
and it's actually very special to the system and not present in twisted bilayer graphene. It's the physics of large twist angles, like really large, like 45 degrees. And it turns out that this physics is really related to the order parameter, and quasiparticles here don't matter all that much. So this idea actually has appeared way before the boom of Twistronics in the last few years. It has appeared already in the 90s. And at that point, people were concerned with determining what kind of order parameter do we have in the cuprates. And people were not thinking about monolayers at all. So a lot of the physics I'm going to discuss in this section actually works perfectly well if you take two bulk superconductors. But those superconductors, let's assume they're a D-wave, as by now we're fairly certain the cuprates are. And let's see what happens if we'll make an interface between two bulk D-wave superconductors. So in that case, I mean, superconductivity will happen in each of those samples on its own. And the order parameter is a complex object, as I discussed a few slides ago. But the phase difference between these two order parameters isn't fixed. So it's completely free unless I make the interface work. So what interface does, it actually couples the two order parameters describing two samples, and allows me to determine also the observable quantities such as the current. And before long, you will notice that if I couple the order parameters in the simplest possible way in Ginsburg-Landau theory, and I calculate the current flowing along the interface, I find the relation between the current and the phase difference. That's the well-known Josephson relation. Unlike the simple case that you see in the textbook, the critical current, the prefactor, should be dependent on the rotation angle, because it's clear that this picture changes when the top order parameter starts to rotate. And the statement specifically allowing you to determine that your superconductor is D-wave is the following. Let's consider this rotation angle to be 45 degrees. Then when I look from the top, the two order parameters are rotated like this. But also, if I look at my system, there's a new symmetry emerging. I can basically rotate the two layers by 45 degrees and then make an inversion. This is so-called roto-inversion symmetry, which happens precisely at 45 degrees. So this symmetry does the following. You can see that one of the order parameters, blue goes to blue, but the other order parameter, red goes to blue. So you can see that the sign of one of the order parameters under the symmetry changes. So this coupling is completely forbidden, and therefore the critical current, the Josephson current, flowing across the interface at 45 degree twist should be exactly zero for D-wave superconductor. Notice there's an ellipsis here, which I'll discuss in a few slides. This is the lowest order expansion. So in Landau theory, this means that there will be orders of higher and higher terms of higher and higher order in the order parameter. So the experiments have been done already at that time, and the puzzle was that they were completely inconsistent with D-wave pairing. So if you look here, that's one of the first systematic experiments. People have measured the critical current as a function of twist angle on the junction, and you can see that actually most of the data points are completely independent of the twist angle, which is more consistent with something boring and uniform rather than with highly anisotropic D-wave pairing. Some newer experiments see a little bit more of a spread developing around the 45 degree angle. So this axis is essentially the critical current. But still, a lot of groups still to this day interpret those experiments as evidence of S-wave superconductivity in the cuprates. And what's special about those experiments is that the samples required annealing at very high temperature, which means that the interface may be reconstructed in some uncontrollable and unpredictable ways. So what the group of Philip Kim has achieved is to create those interfaces at cryogenic temperatures and inert atmosphere. And that actually circumvented the need for annealing. The samples were superconducting as made, and you didn't need to anneal them to make them superconduct, so you can perform the measurements right after the stacking. And what you can see, this is the critical current as a function of twist angle. Indeed, the critical current goes pretty quickly down, and it becomes very small around 45 degrees. What we did recently, we just assembled all the data from the literature available to this day. So the empty symbols correspond to the samples that had to be annealed. You can see that they're kind of scattered a bit. So it's hard to say. The samples from Philip Kim's group that I've shown you are the purple ones, and they're really nicely go down at 45 degrees. But the other groups, actually, if you look, there's quite a bit of a spread of data still up to this day. The overall idea is that there is still a suppression at 45 degrees, but there's so much scatter that one needs to be really careful about those interfaces. And the triangles, actually, I recently talked to that group, and they improved the quality of the interfaces, and the value of the critical current seems to be going up at zero twist. So I think there is kind of an ongoing progress in making those interfaces better and better, and I think it's important, especially for the things that I will discuss in the second part of my talk. Okay, so far, basically what I try to convince you that cuprates are D-wave. Perhaps that's not so very interesting. So the point that is more interesting is that as you go to 45 degree, the only thing I told you, that the lowest order coupling across the interface vanishes. That doesn't mean that the higher order ones cannot be there. And indeed, these terms are allowed, and they would generate an additional critical current, so you would see some superconductivity. And the physical meaning of this term, if you wish, is the co-tunneling of two Cooper pairs simultaneously. By itself, it just tells you that there would be some superconductivity across the interface, but you can also relate it, as I did a few slides ago, to the energy stored in this junction as a function of phase difference. And while the lowest order term, cosine phi, always favors the phase difference to be zero across the interface, which kind of makes sense, you want to have a uniform superconductivity, the second order term, dominating at 45 degree, actually favors a non-zero phase difference, and if you cross out this term, the phase difference that is favored would be plus or minus pi half. So you have a choice to make, the system has a choice to make, and the way it makes it is random, which tells you that there is a spontaneous breaking of a symmetry. So you choose either that potential well or that potential well. What kind of symmetry is broken? Let's remember that the time reversal operation in quantum mechanics is essentially equivalent to complex conjugation. Therefore, if you are creating a complex phase that you cannot get rid of, and you have two different minima with non-zero complex phase, that means that each of them breaks time reversal symmetry. So what is expected is that at 45 degrees, not only you will have some critical current remaining, some superconductivity across the interface remaining, you also expect the interface to be time reversal breaking. So there are two ways you can convince yourself, two steps. So first step, you want to convince yourself that the relation between current and phase is exactly doubled with respect to ordinary case. The way this is done, or at least one way you can do this, is to probe the dynamics of the system. And with the well-known second Josephson relation, basically the time evolution of the phase is related to the energy difference for the Cooper pairs across the interface. And in the ordinary case, one Cooper pair tunnels, so you have 2e here, and you expect a resonance to occur at voltage that is related to the oscillation frequency of the phase. And the oscillation here is created by hand. You just send an AC current through your junction, and what happens is that you indeed see pronounced anomalies at the voltage that's equal to integer number of those frequency steps. Now, if you have two Cooper pairs tunneling simultaneously, instead of 2e, you get 4e, so you expect steps also appearing at half integer voltages, and that's indeed what happens for samples that are close enough to 45 degrees. So this one is actually quite a bit closer than this one to 45 degrees. Those signatures are quite smeared, But if you do the actual simulation, you notice that even if the second harmonic current is 5 times larger than the first one, those half steps are indeed quite a bit smeared, especially in presence of noise that's inevitably present in an experimental setup. So it's quite consistent with the second harmonic being present and maybe even dominant, close to 45 degrees. But that doesn't quite tell you that time reversal symmetry is broken. So formally, the sign of this term is not fixed by symmetry. So there are two alternatives. Either the potential will look like this, where you'll have two different minima, breaking time reversal, great. Or the potential, if I revert the sign of this term, will look like this, and it will be boring. So how to distinguish that the system really prefers to break time reversal? The idea is the so-called superconducting diode effect, that we will apply the current to the system, which actually biases this potential. And if we're in a situation where the system chooses one of the symmetry breaking states and will bias the potential to the left or to the right, we will see a different value of the critical current where this potential will become essentially unstable. So if we bias it to the left, you can see that actually the phase will start rolling out of its minimum earlier than when you go to the right. Well, you have to overcome a much bigger potential barrier. So the way this is done experimentally is that you start with a very large current bias, where the junction is no longer can sustain a superconducting current, and then you gradually reduce it. At some point, you go back to the superconducting state. Then you increase the current, and you get to the maximum current that the junction can sustain. You again get voltage. You do the same experiment, but after going into superconducting state, you actually increase the current in the opposite direction. And then what you need to do, you need to compare the values of those critical currents in two directions. You can see that they are different. And in principle, it is consistent with broken with time reversal broken state. But since I told you that it has to be spontaneous, we should also be able to train that state, to train the direction of the diode by cycling the current. The way it works is like this. You send a current pulse at your interface. And after sending that current pulse, we assume that the system has prepared itself in a state where the phase has a particular value. And then we're applying a current, that's the dashed line, and we see some voltage in one direction, but not the other. This is some particularly chosen value of current that is larger than the critical current in one direction, but not the other. To show the training, we do the following. We do the same kind of protocol, but we reverse what's happening in the preparation step. So basically, we just drive the current in the backward direction. So because it's just the same protocol but time reversed, we expect the direction of the diode to be exactly the opposite, and that's exactly what happens. So if we still apply the current in the same direction as the previous time, we see no voltage, but we see voltage in the opposite direction. So what has been observed experimentally is indeed that A, we have second harmonic, which is consistent with a phenomenological theory prediction, and B, that there's a trainable state which prefers one direction of the current versus the other, consistent with broken time reversal symmetry. Okay, so this effect has been proved in a multitude of samples having different twist angles and so on, and what you can see is that the efficiency, this is like the diode effect efficiency, actually goes down at 45 degrees, where I just try to convince you that time reversal symmetry breaking is the strongest, then it goes up, and then finally it goes down when you go far away from 45 degrees. Turns out that if you do actual calculations, without going into details, we just model the junction in a well-known RCSG model, which you have a Josephson junction, but in parallel you have quasiparticle resistance and some capacitance of the junction because it's like a parallel plate geometry. So if you do the calculation, you find that not only at 45 degrees exactly the diode effect has to vanish. There's a reason for that, because if at 45 degrees you just have the cosine to phi potential, and actually if I sit in this well or that well, locally for this particle, left and right are the same. There is a reflection symmetry of this potential. This is not true here. For this particle, going to the left and to the right is different, but not in this case. So indeed at 45 degrees there's a reason that the diode effect can vanish, But what we also demonstrated that actually, if you see diode effect, that means you do have time reversal braking, but actually it is possible that, all of these curves are in the time reversal broken phase, but some of these curves show no diode effect for a long range of twist angles, which means the diode effect is sufficient, but not necessary criterion for time reversal symmetry breaking. And one of the directions I'm kind of working are different probes of time reversal breaking in the systems that will allow us to characterize this phase better. That includes second harmonic generation, which turns out to be necessary and sufficient, and photocurrent probes. Okay, so far I talked to you about the physics of the order parameter, and I didn't even mention electronic physics, the physics of quasiparticles, and no magic angles, nothing like that. Some people call 45 degrees the magic angle, but I will show now that there is actually a magic angle similar to graphene in the system. So far, we find that the presence of the order parameters actually endows these twisted systems with new emergent physics at large twist angles, let's say 45 degrees, where twisted graphene would be actually boring because the Dirac cones will decouple. Now I will go into the territory more close to twisted bilayer graphene, and I will try to understand what happens with those Dirac points as I twist. And okay, just a few details for the, I guess, experts in the audience. So the way you do this, theoretically, is you want to construct some low-energy model, which really takes into account just these two Dirac cones, but you also need to be careful about how to take twist into account. So the way this works, you take the brilliant zone of a single layer, and you take the other layer, and you take all possible brilliant zones, and you rotate them with the twist angle. And what happens if you want to consider the actual problem is that you tunnel between the two layers at momenta which are overlapping in this figure. So that means that for this point, for example, I need to take into account the first brilliant zone. In the second brilliant zone, it will overlap with a somewhat different point in the other layer, and so on and so forth. And in twisted bilayer graphene, this is very crucial because the Dirac points are at the corner of the brilliant zone, so there are many, many processes like this, and the problem becomes complicated. The difference in twisted nodal superconductors is that those Dirac points are not fixed to be at any high symmetry point of the brilliant zone. They have to be along a high symmetry line, but they can be pretty close to the origin, which allows to neglect all these higher order processes and just limit yourself to one tunneling process which couples those two displaced Dirac cones. That's that. So those pairs of Dirac cones, so in this picture, there's a Dirac cone on every diagonal and in every layer. So there are 4 pairs of Dirac cones. Each pair forms an independent valley, if you wish. And what I'm going to do in the next slides, I'm going to tell you what happens in each individual valley first. So the simplest model you can construct, which I'm going to turn to for the purpose of presentation, is that if we start with a circular Fermi surface, the rotation doesn't do anything to the Fermi surface, but the rotation clearly changes the position of the zeros in the superconducting gap. And at low twists, you can essentially substitute a rotation by a shift. And what happens is that you just take 2 instances of the same Hamiltonian for the Dirac cone, and you shift it in opposite directions in 2 layers, like θ half minus θ half. And you allow for the tunneling, just single electron tunneling, nothing fancy between the 2 layers. So that allows for a very simple complex form for the Hamiltonian, which you can solve and understand basically everything about it. So you have Dirac cones. Tau 3, tau 1 are particle hole space. Tau 1 is the superconducting order parameter coupling particles and holes through the condensate. Then there is a term associated with the twist, which shifts the position of the zeros of the superconducting gap in opposite directions in 2 layers. And finally, there's a interlayer, sigma stands for layer, interlayer tunneling of electrons and holes. So that's just a 4x4 matrix, which you can diagonalize, and I will walk you through what happens. At 0 twist angle, what happens is that you hybridize the 2 layers, and you get a bonding and anti-bonding Fermi surface, and basically there are Dirac cones where the nodal direction crosses those bonding and anti-bonding Fermi surfaces. And those Dirac cones are more or less equivalent to the ones found in individual single layers. Something interesting happens when you turn on the twist. Those Dirac cones come closer together, and the velocity of those Dirac cones is renormalized, and you can see that it goes down, and there's actually a special value of twist angle where it's supposed to go to 0. Notice that those Dirac cones are not isotropic. They can be horrendously anisotropic. The velocity in two directions can be 10 times different, but they are renormalized in exactly the same way. And that just falls out of that equation. The magic angle in this case is equal roughly to the ratio between interlayer tunneling and superconducting gap, the maximum superconducting gap in each layer. So let's say for cuprates, that's a very small quantity. And I will show that the estimate for this magic angle is around 3 degrees compared to 45 degrees I've been talking about in the first part of my talk. Okay, so what happens at the magic angle? In this model, you just know the answer. And the answer is that these 2 points collide, forming a quadratic band touching. And as you go to a twist angle larger than the magic angle, this quadratic band touching again separates into 2 Dirac cones going in opposite directions. So there's just one magic angle. What happens here is that you have a quadratic band touching, and the density of states for a quadratic band touching is actually finite, even right at 0 energy. So you have a bunch of, density of states, all jumbled in one single momentum point. You would naturally expect this to be unstable. And I'm going to quickly walk you through what the prediction is. So you can actually analyze different instabilities that this quadratic band touching can be prone to, and assuming that the interactions within each layer are much stronger than the interactions between different layers, you find that the only instability that this thing is prone to is the development of a secondary superconducting order with a phase difference with respect to the first one, which kind of reminds you of what happens near 45 degrees, but for a completely different reason. Here, it's the physics of quasiparticles that get flattened out, and if there's some residual interaction between them, they can develop the secondary superconducting order. The prediction is that this should be close to the magic angle. As you twist away from it, you're going to lose this secondary phase. And we made some estimates for different materials. And in some sense, this tells you that, yes, some sort of physics of twisted, let's say, bilayer graphene is also present here. There are no flat bands. So this quadratic band touching, it's continuous. It's not like you form some kind of a flat band that you can, try to write localized states for and so on. But there is still a reasonable discussion of instabilities here. What is most exciting about the systems and different from twisted bilayer graphene is something I'm going to focus on next. And I think, for me at least, that's the main selling point. So basically, the selling point is that at any twist angle, you can simply, on demand, make a twisted nodal superconductor a topological superconductor. The only thing you need is to apply a current. As I described in the first part of my talk, actually, so at this point, I'm talking about a bilayer. So it's not like an interface between 2 bulk superconductors. It's really a bilayer. And I'm sending a current between these 2 layers, which, again, is a Josephson current, which is related to the phase difference between order parameters of the 2 layers. So in the first part of my talk, I was wondering, okay, maybe the phase difference can develop a non-zero value on its own. Here, I'm going to do a much more simple thing. I will say, let's drive a current through the system. Less than the critical current is going to generate a phase difference. That's it. I'm going to introduce the phase difference by hand. What this does to me is this continuum Hamiltonian I just derived acquires a couple of new terms. And most important of these terms, which, as you can see, vanishes for both zero twist and zero phase difference, is a term that has an imaginary component and that corresponds to a superconducting order. So in some sense, we're by hand inducing this secondary order parameter, which is going to gap out the Dirac points. Indeed, this is what happens if you project these terms induced by the phase difference to the original Dirac points. they get gapped, and moreover, they get gapped with the same chirality for the two Dirac points. So if you calculate the total integrated Berry curvature over the two gap Dirac cones, you're going to get 1 or -1. Notice that this gap opens at any non-zero twist angle and phase difference.
That's the question. So
Sure.
you have Josephson current between two planes, but
Yes.
then you must have equal currents flowing right on the planes.
No, if it's just purely c-axis current, right? You're taking it out in the c direction. In principle, you don't have to have anything in the plane.
Oh, so you have contacts throughout the whole sample.
Yeah. Just let's put the contacts in the c-axis geometry.
Interact with your system. It's not a part of the Hamiltonian.
Some small tunneling coupling to external leads.
But it's just as strong as the coupling of these two things to each other.
I can make it weaker.
But the current must be the same.
Yes, of course.
In that sense, it's strictly the same coupling.
I mean, the current is the same, but not necessarily the coupling. I mean, the tunneling can be very weak, and I mean, there could be a big contact resistance, right? So I put some kind of insulator on top of that, right? Not too thick, so it would be completely insulating, but thick enough so I can ignore the hybridization with the wave functions of the leads. And between these two, there's nothing, right? So they're really close to one another, so the wave functions here hybridize as good as they
Even
can.
without the currents, if
Of course, yes. But the
Can
point
you
is,
send the current to zero?
what? Sorry.
Can you send the current to zero?
Of course, yes. So the whole point of this proposal is that I send the current along the c-axis between these two layers, and something interesting happens.
But can this current be arbitrarily small? Or
Of course, yes.
So you don't care about, you don't have any critical current. No matter how small the current, it's the same physics.
Exactly. What I don't want to send too large current, because then I get dissipation and I don't know what to do.
Why don't you have your physics when current is exactly zero then?
Because time reversal is still intact. I need to break time reversal. There will be a symmetry argument in a few slides.
But so time reversal doesn't break on its own.
Exactly. So I'm breaking it by hand.
Oh, but then you cannot have arbitrary weak current.
Why not? Arbitrary weak current, arbitrarily
means
weakly means breaks time reversal.
Oh, you mean you will have arbitrary weak breaking of time reversal. Then you will get arbitrary weak observables.
Exactly. Yeah.
Oh, no. But then it comes back that to have observables, you need a sufficiently strong current. But then exactly the same current connects to the upper and lower electrodes. And what's the effect of that? How do you know that this effect is not comparable?
Basically, just because I can make it a different material, right? So that the wave functions will not hybridize. I can make it, I don't know, aluminum or whatever context I want. I don't have to. Whereas here it's like the same material, right? And there's nothing in between.
It's not obvious for me. There is something else in the Hamiltonian that appears to be large, as opposed different.
Okay, yeah, I see. At least the current is definitely the same. Okay, now there will be actually a contactless alternative in a few slides too. Okay, returning back to this problem. So what I'm saying is that you can actually generate a phase difference by hand in the system, and that phase difference, what it does to you is that it opens a gap at the Dirac points, and this gap is actually non-zero at any twist angle. And at any twist angle, you can actually, by sweeping the phase difference from 0 to pi half, that's the maximum you can get, in the Josephson junction by applying current, you can see that the gap is actually growing on increasing the twist angle. It becomes of the order of interlayer tunneling at around the magic angle, not exactly at the magic angle, and then it goes down as basically 1 over twist angle. This is for a very specific model with circular Fermi surface. If you take a more realistic one, however, one that's appropriate for BISCO, actually you don't see too much of a difference. The main difference is that at large twist angles, the gap goes down dramatically, but the maximum and the width of that peak is not changing a lot. So it's a very robust feature. This topological gap is present at a range of twist angles, and unlike graphene, where if you miss your magic angle by, 0.1 degrees, you're done. Here you miss it by 0.1 degrees, you couldn't care less. One thing that I want to mention is that I've been treating so far just one pair of Dirac cones, but I have a whole Fermi surface, And if you remember, there are actually four pairs of those Dirac cones, each doing its own thing. So in the interest of time, I'm just gonna say the result. If you just analyze what happens to every single Dirac cone on the Fermi surface, you will find that its contribution to the total Chern number, to the integrated Dirac curvature, is the same. So actually, you are getting a topological superconductor. You are expecting a gapped bulk and a gapless boundary. And in principle, if you introduce vortices, you also expect zero energy modes in the cores of these vortices. This happens at any twist angle, any phase difference. So this is kind of seems too robust to believe it, unless there is a symmetry argument. And of course there is. So if you start with the square lattice, where d-wave order parameter is well-defined symmetry the order parameter can have, there's actually another d-order parameter that's obtained by rotating this one by 45 degrees. And they are distinct in symmetry. Specifically, mirror planes that I've drawn here change the sign of this order parameter, but not this. Now let's twist. So if I look at this picture, it doesn't have those mirror symmetries any longer, which means that those two order parameters are no longer distinct, and they're allowed to mix. But since I have time reversal symmetry, I'm not allowed to make any complex phase difference between the two, and that's what the current does for me. Once I apply current or any other time reversal breaking perturbation, I can actually mix d-wave superconductivity x squared minus y squared and dxy with a complex phase in between. And this kind of order parameter is well known to be a topological superconductor with a Chern number of 2 per each layer. I have 2 layers, so it's 4, and it has all the properties you expect a topological superconductor to have.
Can I ask a question? So you have quantized thermal conductance. Now let's imagine that the current goes to 0. You still have strictly the same quantized thermal conductance, no matter how small the current is. And yet, when current goes to 0, it should disappear.
No.
This can happen only if you have vanishingly, if the gap depends on the current.
Exactly. Gap does depend on the
So
current.
how does the gap depend on the current?
Of course. Yeah, here we go.
Oh, I see. Okay.
So the gap will smoothly go down to 0, and that would be the end of it. Okay, so I guess one more point to address your...
How broad are the edge states? What is their width?
That is basically, your topological gap divided by the velocity of the Dirac velocity. So it actually will be, I think, also anisotropic, depending how edge is oriented with respect to the major axis of the crystal. But overall, yeah, that depends on the size of the gap. So basically, like delta divided by V Fermi over V delta.
V Fermi divided by
V Fermi divided by
I
delta,
see.
of course. Yeah.
So what happens when the current goes down? The edge state becomes broad.
Yes, and then
So
the bulk
really
also
happens-
closes.
Oh, I
Yeah.
see. So what really happens is not even the issue of the gap. You will still have a finite gap, but the edge state becomes so broad that you no longer have edge protection.
Yep. Yeah.
Okay, even before you close the gap as well. Okay,
Right.
I see.
So one way to avoid some of the questions I just got is to avoid current altogether. Okay? So, and it's possible to do this by applying an in-plane magnetic field in this system. And because I have two layers of a superconductor, I can think about this as a Josephson junction. And what is known about Josephson junctions, if you apply in-plane field, you actually generate vortices, like in any superconductor, but these vortices are different from your usual abricosive ones in the sense that their core is like between the two planes. So you're not suppressing the magnitude of the order parameter, you're just widening its phase. And what you expect then, like from any vortex, there will be current going between the two planes, up here, down here. And as I just told you, applying current between the two planes should open a gap. So picture is you will have topological domains. To the left of the vortex is going to have one chirality, to the right of the vortex is going to have a different chirality, but the edge modes coming from these two domains go in the same direction. So they will not gap out, they should be stable. And this is indeed what a calculation tells you. So if you consider a vortex lattice, like an infinite system, you can actually calculate the band structure of quasiparticles in the system, and you find that there is a band of those vortex modes that's separated by a gap from the rest, from the bulk, and that band is chiral in the sense that you can see that the dispersion along the y direction, there are distinct states dispersing in one direction and the other, and those states are actually localized. So let's look at this one. That's the green one. So if you plot the density of states, they are localized at one position where the current vanishes. And if you look at the states dispersing in the opposite direction, they're at the nearest neighbor position. So it's really like in this picture. The states along this vortex core go in one direction, but the states along that vortex core go in the opposite direction. So, and you can basically induce this by magnetic field. You don't need any contacts. And then you can come, for example, with an STM probe and see that the inside of this region is gapped, but the density of states at the vortex cores contains those gapless density of states, and it's precisely those that are also carrying the chiral currents. Okay, let's see. So with the time that I have, I'll just briefly mention some offshoots. We considered doing a twisted bilayer at this point experimentally is a great challenge. So I think, despite I shown you a monolayer that's superconducting as the bulk, taking two monolayers and transferring them on top of one another with a twist turns out to be much more challenging than for graphene. People are working on it, but it's hard. So what we did is, okay, let's simplify the life a little bit. Let's take a stack of layers, just a flake with finite thickness, and then put one layer on top with a twist. And I mean, you can also put many layers on top with the twist. We thought about that too. But that's the basic setup, and we wanted to check whether any signatures of topology survive in this case too. And what we found is that there are two competing effects. On the one hand, your gap, which is formed essentially due to this interface, is delocalized, is smeared out throughout this flake. It proximatizes at all, that's true, but the average gap goes as 1 over the thickness of that many layer system, so 1 of the number of layers. On the other hand, the number of edge modes grows as you get more and more and more layers. So actually at intermediate temperatures, not where the quantized plateau is, the thermal Hall effect, for example, will be independent of thickness. And also, if you measure at the top layer, we found at least numerically for a few layers, the topological gap that you will see at the top layer is pretty much independent of the number of layers you put in. And one of the really crazy results is that if you do the same thing I told you about, applying a current going through the stack, we see topological transitions. This is Chern number. This is current in units of critical current. And as you add more and more layers, so for a few layers, you go up to critical current, the Chern number is the same. But if you go to more and more layers, there are these transitions, jumps in the Chern number. And at least mathematically, if you believe this model, you can show that you can get up to Chern number of order n squared. So you have n layers and n squared edge modes. I mean, believe it or not, the model is pretty simple. It's kind of a non-interacting BDG model. And I think at least maybe the lowest of these transitions can be possibly seen in the experiment. Okay. So that's maybe all the things I wanted to tell you about twisted nodal superconductors. Do I have like 5 more minutes, or should we go?
Yeah, sure.
Okay. So one thing, if there's one thing that you get away from this talk that I want to really deliver here, is that a lot of this physics is actually can be described. I mean, we've done the calculations, that's fine. But a lot of it can be understood with simple symmetry arguments, right? You break certain symmetries, and then you allow certain combinations of the order parameters, boom, that's that. So I started to think at some point, is it possible that actually a lot of magic of the moire materials comes really from the symmetry properties of twisted bilayers? And, to prove me right or wrong, we've taken an extremely boring system and add a twist to it, and we basically try to explore, okay, we'll take a boring system, we add twist to it, does it become interesting? Does anything become interesting with a twist? And the answer is so far on the yes part. So what we analyzed is what happens to the flat bands So that's a single layer. That's the dispersion of electrons. Tight binding model on a square lattice. It has a minimum at zero momentum, has a maximum at the corner of the Brillouin zone. And then you look at these moire bands that form around this maximum. And let me go through. So what you see is the following. You indeed form a flat band at low twist angles. But if you analyze, that flat band has no topology. There's nothing too fancy going on. But if you look at the tight binding description of that flat band, you find that the nearest neighbor hopping on the moire lattice is exactly 0. So basically what you find, I mean, I've taken the most boring model you can imagine in the moire business, and what I found is that completely counterintuitively, there is no tunneling between electrons localized here and here. And there is some tunneling between those here and here. And those two sides are, of course, closer. So tunneling is exponentially suppressed always, so you don't expect this to happen at all. What we found is the following. That, okay, we constructed a continuum model, which is just two parabolas displaced from one another by a certain vector that's related to twist. There's an interlayer tunneling. And you can show that that continuum model has an emergent symmetry. Let me say a few words about this. If you have an untwisted bilayer, there is a mirror symmetry. Those two layers are the same. Now I twist, that's not a good symmetry any longer. But in momentum space, there's an analog of the symmetry, a vestige of that symmetry that still remains. You have two parabolas, they are displaced, they're in different layers. Now you can interchange the layers, but oh, the parabolas now are not in the right spots in momentum space. So I need to shift them back. And that's what this exponential does to you. It shifts them back, but in real space, it's modulated. And you can actually show that this exponential takes on values of 1 or -1, sigma z doesn't nothing, inside each of the moire sides. So basically, my wave functions that are localized on this side under the symmetry, which is the symmetry of the Hamiltonian, they change sign. This becomes +1, this becomes -1. So nearest neighbor hopping is forbidden by this layer symmetry. This layer symmetry is not exact, but the corrections to this layer symmetry are actually of order twist angle to the 5. So it's really a good symmetry at low twist angles. And once we understood this, we realized, okay, well, you can break it actually by hand. And specifically, you can apply a displacement field, make the chemical potentials of the layers different. And what we see is that actually we can induce a nearest neighbor hopping on this lattice that becomes sizable. So this, in this case, it's 5 times larger than the next nearest neighbor ones. And why all of this may matter is that we're having, if we had interaction, a Hubbard model where you can tune the ratio between nearest neighbor and next nearest neighbor tunneling. And that turns out to be a super crucial parameter. Without next nearest neighbor tunneling, there's no superconductivity. And if you look at old numerical simulations, they actually conservatively go up to 0.3. So T prime is smaller than T by almost 3 times. And now we have a model or a system where you can realize T over T prime 1, 20, whatever, because initially T is equal to 0. And things that can be realized when you go to large ratios of order 1 are spin liquids, higher temperature superconductivity, and other fancy things. And actually there are materials candidates for those twisted square materials, and we're hopeful that something will come out of it. So to conclude, I talked about the physics of twisted superconductors, so taking superconducting materials in monolayer form and twisting them. And it turns out if you take nodal superconductors with anisotropic order parameters, you can get a lot of new physics that basically can be either introduced by hand, like driving currents or magnetic fields, or by twisting to very large twist angles where you wouldn't expect anything interesting to happen in systems like graphene. The materials are readily available. Now everything is focused on BISCO, but one of the things we tried to achieve in our review is to motivate developing other material platforms. some of transition metal dechalcogenides, maybe unconventional in monolayer form. And as a crazy idea, of course, you can take something like twisted bilayer graphene and try to make a twisted junctions of those unconventional superconductors. A lot of this physics can be actually attributed to symmetries, specifically point group symmetries. And what I'm interested in at this point is trying to apply this idea to wider classes of materials, because it actually makes you, allows you to make unbiased predictions, no matter what material this is. If the symmetry gives you interest in physics, it should be there in any materials. Thank you very much for your attention.
Yeah, so maybe you can explain to me. So when you start writing down the BDG Hamiltonian for these stacked superconductors, I'm a little bit confused at how it's qualitatively different from the Fitzgerald-McDonald model and like regular TBG.
Yes.
It looks exactly the same.
No. So it's actually simpler, surprisingly. The difference is the following. In Bistricer-McDonald, you actually have not just two displaced Dirac cones, but there's actually three relevant tunneling directions because you're at the corner of the brilliant zone. So you actually have to add another two, and when you do that, you actually can even hop further in momentum space, and you go on and on and on. So in principle there, it's not possible to solve the problem exactly, so you either do perturbation theory or solve it numerically. This thing, you can neglect all those other couplings because they arise from tunneling in higher brilliant zones, and they are exponentially suppressed with respect to this one, as long as this point is close enough to the gamma point of the original brilliant zone. But there is some kind of a small parameter, which is there, so you can actually neglect those, and once you did that, you get the Hamiltonian that you just solve.
So the qualitative difference between this, if you eliminate those higher terms, is just that you don't get a flat band. You get some.
Yes. So basically, that's basically the price you have to pay. That you don't get flat bands, and that's another direction which I think is interesting to see whether you can actually try to engineer somehow actually flat bands for superconducting quasiparticles. This model just gives you hybridizing Dirac cones, but they're continuum. There's no kind of cutoff. Other questions? Yes.
So I can imagine that, like, if the Fermi surface here, like if the arcs that the Dirac cones live on are sufficiently close to the corners, then there's going to be some like region of, or some range of twist angles where they don't overlap, right? Like
Yeah.
45 degrees. So I guess, like, is it like tunable enough that you can see that? I guess I'm not like a.
Yeah. So actually, that's one of the, I would say, kind of points I've worried about a lot, specifically when doing this calculation, because if you rotate a circular Fermi surface, it still overlaps with itself perfectly. But if it's not circular, you start rotating, it's like doesn't even cross. So I was really worried, like, whether all these gaps and so on will go away, and they kind of do, but at large twist angles. And I think it's actually there are some additional specific points whether the topological gap even survives at 45 degrees. I think some of the initial proposals were exactly that. Okay, let's twist to 45 degrees. It breaks time reversal spontaneously, creates a phase difference. Maybe we can get topological superconductivity. I think the discussion that has been happening in the literature is, okay, so what's the size of the topological gap there? Our contribution is more like, okay, so if you actually go to the low twist limit, you see that the maximum is somewhere there. What happens in high twist angles, that would be highly model dependent. I mean, there will be some perturbative effect, but it will be suppressed.
So you showed the result for the square lattice. You're saying that you pick a most boring lattice and you twist and you get this extraordinary result. But this is specific to square lattice, right? If you do honeycomb lattice, then you don't have something similar to this.
Not quite. So the degree of freedom that does the heavy lifting here is the momentum of the electron in the initial brilliant zone. So in some sense, that's a wrong picture, but if you imagine, so if I plot the wave function at this point, it's like changing color every other side. Mm-hmm. And then if you take two of this and twist, you will see that there's actually a big difference emerging between nearest neighbors. So the heavy lifting is done by these electrons actually having non-zero momentum within each layer. And on a hexagonal lattice, there's also an M point. There are actually 3 M points. And there have been works from Bernoulli group, which actually have seen kind of the same thing happening, but on a hexagonal lattice. So there's the same effect, but what you get there is you get 3 quasi-one-dimensional moire bands, which don't talk to one another. And they're quasi-one-dimensional specifically because the lateral coupling is forbidden by the same effect. Now, let's say K point would be different, but there will still be consequences of the symmetry at any like high symmetry point. It's just one needs to figure out which consequences exactly.
So is this effect robust against lattice relaxation?
I would believe so, because my understanding, as long as you keep symmetries and moire period intact, the only thing that's going to happen at the continuum model level is that you can renormalize these parameters, and maybe you can make some higher order terms also relevant, but they don't break the symmetry. That's the important point. There are actually other effects that come they're exponentially suppressed by 1 over twist angle e to the minus 1 over theta, that actually microscopically, if you really look closely at these 2 sides, I don't know if you can see it, but they actually microscopically differ. So here, the middle of this unit cell, you have empty, and here you have an atom. And previously, when people studied this in tight binding model, they attributed all these effects to this actual real doubling of the period. In our continuum model, this is erased, and the effect is still there. So what we found is that those things will matter at high twist angles, but at low twist angles, they are suppressed, as I said, by e to the minus 1 over theta. So,
Okay, maybe I ask one question. So when you mentioned these condensed thermal conductors, I wonder what is the maximal temperature where this will be seen in realistic system?
Yeah, just give me a second. Basically, you need to be well below the gap, the topological gap. Here's the plot. So well, that's that. I mean, actually, like the quantitative thing would be you go below the gap, you see the quantization. But if you look at the numbers are actually